Did you find my video clear? Please acknowledge, sir. Okay. Yeah. Good morning, friends. Uh, in the today's session, we are going to discuss COA and some tutorial questions we are having here. Okay. Some of the topics I am going to cover today, and the remaining questions or remaining topic are going to cover tomorrow. Okay. So let me start with some basic things about this. Basic things about this subject, so you can able to understand how you are going to approach this subject, particularly in the gate examination. Okay. So for this subject, before getting started, you must have some information like the number of marks is it is going to cover in the gate examination, the importance this particular subject or topic has, the number of topics or the name of topics we are going to cover today, and what is remaining tomorrow, and the toughness about the subject. Okay, so let's start with the weightage of the subject. Okay, so about the weightage of the subject, this is actually around 5 to 8 marks in the gate examination. The COA subject has 5 to 8 marks of weightage in the gate examination, but in the year 2020, that means this year, it actually got covered 11 marks. Okay, so this is the highest weightage in any particular year the COA has. Okay, so in COA in this year actually COA got covered 11 marks individually. So this is a good sign that it might come uh, with this much of weightage in the next year also. Okay, but otherwise in the in the previous years it got covered only 5 to 8 marks, sometimes 5, sometimes 6, and few times 8 marks of questions are there. Okay, but in the year 2020, this is actually covering 11 marks. बंद हो गया. Freeze हो गया. The video got freeze, I think. Sir, the system got freeze again. Hello. Oh, I am going to restart just. Okay, let me check, sir. It is already started. Okay, okay. 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 The somehow system got freezed. Sorry for the interruption. Let's come to the importance of this particular subject. Okay. Importance about this subject. Actually, let me come to this point first, because some of the EC guys will be there in the session. So I'm going to cover that portion of COA that comes in the EC as well. Okay, so the full topics are going to cover for EC, and half of the topics are going to cover for CS. The remaining CS portion is going to cover by tomorrow. Okay, in the tomorrow session I will cover the remaining of the CS portion. So today EC guy can join, okay, and have this teaser or the tutorial session. Fine. The weightage of the marks I'm going to cover, and the importance of this particular subject I'm going to cover for CS guys mostly, but for the EC, this is going to be for the first time. Okay. So about the importance, of course, in the case of CS portion or CS subject, fine. The importance of the subject is going to cover in programming. In few subtopics of programming are going to cover or going to match with this particular subject, like pointers, memory allocation. These are the few topics or functions that are actually got linked by the architecture or the organization, the COA, computer organization and architecture. Other than this, operating system is again has so much common with this particular subject. Other than this, for EC guys also, electronics guys, digital electronics is again one topic that actually linked with this particular architecture and organization topics. Okay, so CO is got linked via programming, especially pointers, memory allocation, and functions. Okay, most of the topics with operating system, and digital electronics is again the topic that actually got linked with COA. Okay, so if you have a thorough knowledge of this particular subject, it is going to help in these important subjects or topics as well. Fine. About the topics that we are going to cover today are addressing mode, pipeline, okay, instruction format, control unit. Okay, so these are the some of the topics that we are going to cover, or we are going to see some questions about them. Fine. About the toughness of the subject, so most of the people or candidates usually found this particular subject quite tough and lengthy. So I'll give it as quite lengthy and tough, but it is only get tough if you don't have any knowledge, or if you don't have any conceptual knowledge about the question. If you know the conceptual about of the question, only problem is this particular topic comes with numerical types most of the time. So if you got that right, only then you can have the uh, chance to get the correct marks or the maximum marks you can achieve. So the main issue with this topic is the most of the questions they come in the numerical. Okay, so you don't have any choices for them. So this is going to be some tricky. Okay, so quite lengthy and tough, but actually the toughness relies on the knowledge of the concepts. So if you have the knowledge of the concept, it might not get that tough. Okay, so most of the toughness is because of numerical based questions. फिर बंद हो गया. Should I restart it? Again, the screen got freeze. I don't know what is happening. Some heavy service or processes going in background. That is why it is happening this again and again. Okay. The another thing or another toughness about this question that you need to remember a lot. There are so many questions, so many theory about this, and so many formulas are there, equations are there, that makes this particular subject tough for actually the CS guy. Okay, EC guy might get this easy because they already have some microprocessor knowledge over there in digital electronics and digital signal processing knowledge over there. Okay, so they might get over about this particular subject, and they might get a very good knowledge about this. But for the CS guy, we don't have so much of numerical based subjects, so that is why we face usually the problem for solving the numerical based questions. Okay, but if you have the knowledge, proper knowledge about this subject, you are going to face no problem. Okay, about the programming as well, there are few examples that we can have in this session, so that you can see how this particular subject is going to relate with programming, especially with pointers, how the pointers are going to relate. So let me put some question over here, and you can have your own understanding with this. And after the session, if we have some time, if we got some time, I'm going to explain that particular question. Okay, so I'm giving you this question as an example or teaser of this particular subject, how the this particular architecture subject is going to link with programming part, especially pointers. So I'm just writing some source code over here. This particular question of programming is actually based on the architecture and organization. Okay, so I'm just writing this particular source of code so that CS guy can try, because I maybe the EC guy find it very tricky or tough, but CS guy can try to attempt this question with their own understandings, and afterwards I can explain this question or solution for you. So I'm taking some integer value or integer identifier a with the value initialized by 320, and some pointer which is actually a character pointer pointing to this integer value or integer variable. Okay, just try to write it down or remember this particular question and find the answer. And after the session, if you got some time left, I'll ask you for the answers and the explanation. Okay, then we can see did you get it right or wrong. And I will explain this particular thing, how this question is actually based on the architecture part. Okay, EC guys, ignore this particular code. Okay, we will have different questions or various questions for you also. Just ignore this one. Okay, just let it go, and let's come to the question number one then. Fine. Fine. So our first question for today is, assume a system has an 8-bit instruction placed in a 64 word memory, supports both zero address and one address instruction. If system supports only two one address instructions, then how many zero address instructions can be formulated? This is a very uh, important question regarding instruction format. Most of the time, this question actually arises in the PSUs, not in the gate examination. But again, this is actually covered by the gate examination in different way. So you might have this particular portion of question or this particular pattern of question in the coming years. Okay, in the upcoming years. So this is actually asking about this zero address and one address instruction. So what are these actually? Let me cover this first. Zero address instruction means when you don't have any address field in the instruction format. So suppose this is some instruction format, okay, which actually you want to execute in the CPU. So if in the instruction format, if you have only one field, which is called the opcode, opcode actually indicate the type of operation. Okay, like the mnemonics, that instruction set like add, multiply, and divide, and other shift operators and rotate operations. These are all the opcodes, the type of operation in the instruction. Okay, so what kind of operation you want by this instruction to solve, this is going to be in the opcode. But in this type of instruction format, you don't have any address fields. Okay, so from where it is going to take the operands, like if you need to do a plus b, but for this you will have this instruction format like this only the add. You can only have the opcode, the type of operation in the instruction format, but not the operands. So from where it is going to fetch the operands to get it solved. So for this purpose, the operands are get stored in the stack. The stack is actually the data structure or the memory which is following LIFO pattern. Okay, works on the principle of LIFO, the last in, first out. Okay, so whatever the instruction is going to execute, the operands are going to fetched by the top of a stack. So whatever the elements or variables you are having in the stack as the top, it is going to get fetched by the CPU. Okay, so CPU is going to fetch again and again from the top of stack. Okay, only thing you need to remember is this: when this expression or instruction is going to be in the memory, always remember the first operand, operand 1, is going to be in the stack first, then followed by the second. So at the time you are going to fetch these elements or variables from the stack for the execution, b is going to be out first. Okay, so in the addition it won't make any difference, but sometimes if we have something like this, an expression which is actually depending on some exponent or 2 to the power 3, in this case the output might get varied. Okay, because the base and the power are different. So if you do it at 2 to the power 3, it is going to get the answer 8, but if you going for 3 to the power 2, it is going to get the answer 9. So in this case, if you put the values in the incorrect behavior or incorrect way into the stack, you might get the incorrect answer also. So if the expression is like this, okay, so in this particular expression, if you put 3 before 2, okay, or 3 first and the value 2 afterwards, it is going to get evaluated as 2 gone out first and then 3. Okay, so this might cause some problem. So always remember the first operand goes first, and the second operand or other operands are going to follow them. Okay, so always try to remember this. So this means a, which is the first operand in our case, is going to be in the stack first, then b, and the second operand is going to be fetched first. Okay, so whatever is the order of getting in the stack is going to be reversed by the LIFO principle. Okay, just try to remember, this will help you when you are trying to solve the expressions. But right now this is not in our concern around about this particular question we are having here. Okay, so this is all about the zero address instruction. This is all about zero address instruction format. Okay, in one address instruction format, this means you may have one address field over here. So one is opcode, which is necessary because without the type of operation, you are not going to get solve any instruction. So type of operation will be there, and you can have one address field. Okay, so this address is actually allocating where? Somewhere in the memory or register file. Okay, so this is like if you want to execute a is equals to a plus b. Okay, so here you are having two operands, but here in the one address instruction format, we can only have one address field. Okay, fine. So one address field is actually for the second operand. Second operand is using the instruction format to get stored. What about the first operand? First operand is by default stored in the accumulator register. And the same accumulator is going to be the destination also. This is all about one address instruction format. I am explaining or repeating again. The address field is actually for the second operand. First operand is by default going to be in the accumulator, and the same accumulator is going to be the destination or the resultant. Okay, so this particular expression is going to be like this. Accumulator is equals to accumulator plus b. Okay, so accumulator is by default using, this is actually called accumulator machine. This particular section or this particular type of instruction format is solved by stack machine or followed by stack machine. So these are different architectures or machines that are based on some instruction set or instruction format. This particular is an example of accumulator machine. Before getting to the question, I actually wanted to know about the concept or the concept behind this particular question or the variations we are having. Okay, fine. So these two actually we are trying to use in this particular question. So in this type of particular question, when we are actually need to find the zero address instruction or lower address instruction, we actually have four steps to solve this type of question. Starting from step one. Okay, design the instruction format. Okay, so by designing the instruction format means we actually need to design the instruction format obviously based on the higher one, the higher machine we are having. So here higher machine we are having is one address instruction. Higher machine we are having is one address instruction, because in one address instruction you can able to solve zero address instruction, but in zero address instruction we can't have one address instruction solved because this is not compatible. So backward compatibility is there, like in one address you can able to solve zero address, in two address you are able to solve one address and zero address, in three address you are able to solve two, one and zero address instruction, but this won't work vice versa. Fine. So compatibility is like backward, not forward. So every higher machine is going to get solved the lower instruction format. So in our particular question, the higher format is one address instruction format, which will look like this. One field is some opcode and another is some address field. Okay, we already have this length of the instruction, which is already given is 8-bit instruction place. So this particular instruction is actually 8-bit long, in which we are having opcode and some address field. We actually need to find the length of opcode and address field. To find the value of address field or length of the address field, we have 64 word memory supports both zero address and one address instruction. So this 64 word memory is actually the information about the RAM or the primary memory, which will help us to find the address field length. Okay, so how do you find the address field length? You need to find the decoded value of this particular address field. So it will be log of 64 at base 2, which is actually log of base 2, 2 to the power 6 is actually 6. So the address field will be 6 bits long. Okay. So the number of cells or memory you are having, the power of 2 is going to be the length of that field. Okay. So let's suppose you have 32 instructions or 32 operations. Okay. So the opcode field length will be 2 to the power 5, 32, and the power 5 is going to be the length of opcode. So suppose if you have let's suppose 4 instructions like add, subtract, multiply, and divide. So for 4 operations, how many bits you actually want or needed to indicate this or to denote these operations? So you have 4. That means 2 to the power 2. 2 bits are more than enough to actually indicate these 4 operations. How? So if you have 4 values, that means 2 bits means 0 0, 0 1, 1 0, and 1 1. So this could be add, this could be subtract, this could be multiply, this could be division. So 4 bits are going 4 actually operations are going to get represented as 2-bit representation. So 2-bit in the opcode are going to represent 4 operations in the instruction set. Okay. So if you have 32 instructions, 5-bit is the length of opcode. This is how it is calculated. Fine. So, but here the instruction is already 8-bit long, and we already have calculated address field as 6 bits. So remaining number of bits are going for the opcode, which is 2 bits. So for 2 bits, we are actually going to have 4 operations. Okay, fine. This is actually the step 1. Step 2. After you design the instruction format, find the number of opcodes, total opcodes the system or this instruction format supports. Fine. So how do you find the number of opcodes? You have number of opcodes like the encoded value of the opcode field. So if you have 2-bit representation of the opcode, you may have 4 operations. Okay, so 2-bit representation in the opcode will get you 4 operations. So 5-bit opcode will give you 32 different instructions, and 32 different instructions are going to represented in 5-bit representation in the opcode. Okay. So after 4 operations we are having, these 4 operations are actually reserved for the higher machine, which is in our case is one address instruction format. But we need to find the 0 address instruction format. Okay. It is already given in the question. If system supports only 2 one address instructions, so out of 4 operations we are actually have, out of 4 operations, only 2 one address or higher machine instruction the system actually supports. So the remaining are actually can be utilized for the lower machine as per the compatibility. Okay. So how this is going to be? So we'll start with step 3. Okay. So after you calculated the number of opcodes, you need to find the number of free opcodes. After allocating higher instruction format, which is in our case is one address instruction. So out of 4 total operations, only two operations are actually supported by the system as one address instruction. So after allocating one address instruction, how many opcode bits are actually remaining? Only two. Sorry, how many opcodes are actually remaining? Are only two. So two opcodes are actually reserved for the lower version or lower machine. Fine. And the last but not the least, step number 4. So once you find the number of free opcodes for zero address instruction, the number of zero address instructions are actually equals to the number of free opcodes multiplied by the decoded value of the address field. Okay, so logically speaking, we have one address field which is actually being used by the one address instruction, but zero address instruction, zero address instruction is actually not going to require any address field. Okay, so zero address instruction, for zero address instruction, the address field is going to be empty or unused. So we can use this particular field and the remaining opcode together to find the number of zero address instructions. So higher instructions may be less, but because of this utilization of a reserved address field or unused address field, the number of lower machine instructions might get uh, or maybe it is going to calculate bit more. Okay, so the number of free opcodes, we are actually having two free opcodes, and the decoded value means 2 to the power the number of address field length. So address field length is actually 6, so this is going to be 2 to the power 7, which is actually 128. So 128 zero address instructions are actually supported by this given machine or instruction format. Okay, the decoded value and encoded value, you might wonder about this thing. So the in the simple case, just let me explain. Decoded value means, or the decoding means 2 to the power n, whatever n represents, and the encoded means log of n at base 2. Okay, so wherever you find this decoded value, you are going to have 2 to the power n, whatever n represents, whether it is opcode or address field or whatever the question actually asking for. Okay, encoding means the same value is going to be solved by log at base 2. Okay, so this particular question about instruction format might come in the EC branch as well. So you must have the knowledge about the instruction formats and various architecture or machine based on the instruction set. So there are actually 3 or 4 machines that are actually based on the instruction set that comes in the syllabus. That is first stack machine, then the second one is accumulator machine. This is again the part of EC as well. Okay, because it's actually a new subject for EC guys. So this might come in the upcoming year. The another one is 2 address instruction, and the fourth one is 3 address instruction, which is actually register and registered memory reference architecture. So 4 type of machines are there. One is a stack, another is accumulator, then registered memory and registered register architecture. So these 4 machines are actually in the syllabus, and based on that we can have 0 address, 1 address, 2 address, and 3 address instruction. So if the question arises about to find the 0 address instruction and the system supports 2 address instruction, so first you need to find the instruction format design for the 2 address instruction. Then you need to find the number of opcodes that's supported by 2 address instruction. Then you can allocate 2 address instruction and find the free opcodes for 1 address instruction, and so on. So gradually, by using these four steps, you are going to find how many zero address instruction the machine is actually machine can be formulated, or number of instruction possible in this particular system. Okay, so this is all about this particular question. The stack machine, which is actually zero address, accumulator machine, which is actually one address instruction format. Okay, if you have any doubts regarding this particular question, just note it down somewhere, and we are going to cover in the last half an hour. Okay, in today's session, in the last half an hour, we are going to discuss all the doubts about the number of questions we are going to discuss. Okay, so the answer for this particular question is 128. You can write it down these number of steps, or you may have this video link or PDF after the session is over. Okay, next question is about the pipelining processor. Again, very important subtopic. A number of questions they actually you can actually have in the previous yearbook. So this is the most important topic in the architecture and organization. Okay, the another most important topic is the cache memory. So the number of weightage as a subtopic covered in this particular subject is pipelining, or by the pipelining and the memory organization. Both are very important and very frequently asked question topics. Okay, so let me start with the question. Consider the processor P1 as a non-pipeline processor. Non-pipeline means the parallelism or pipelining is not going to be there, or overlapping is not there. So at a time, only one process is going to get complete, or one program is going into the process. Okay, so this is somehow like batch system, one job at a time. And the upgraded P1, so the same system is going to get upgraded, which has now 5 stages pipeline. So this is now going to overlap, is now become P2. Okay, so P1 as a non-pipeline processor upgraded to 5 stages pipeline and becomes P2 with its respective stage delays. So each stage or 5 stages have their own delays or processing style. And between these stages, we actually usually have some buffer or latch or instruction register like this. Let me show you as a diagram. So let's suppose this is stage one. We are having some buffer or interface register in between. Then stage two, again some intermediate register or interface register, stage three, and so on. Okay, this is how it usually looks. So number of stages we are having has intermediate register in between, so that the output of one stage can get stored somewhere before get into the next stage. Otherwise, the value or the updations are getting lost. Okay, so to get it stored for the next stage, or to get it prepared for the next stage, we are using, or we will use registers here. It might be some buffer or latch. These three things can be used as intermediate memory or space or storage between the number of stages. So the number of time a process or program get into the stage one has some delay. The number of time it is using, or number of clock cycles it is using in stage one, is the stage delay of S1, and so on in the number of stages. Similarly, the instruction register or interface register buffer or latch might have some stage or buffer delays as well. So the data or program staying for a while is going to cost some clock cycles or CPU cycles. Okay, so these clock cycles or extra cycles are noted as delays. So delays here might be uniform and non-uniform. This could be same for all the stages and interface register, or they might get different values or different delays. So uniform means this is actually common for all these stages. Okay. And non-uniform means this is actually different for all the stages and interface registers. Okay, so various stages might have various delays. Okay, this again I'm repeating this thing. This session is actually for both EC guys and CS guys. I'm only going to cover the topics that are actually comes in the syllabus of EC guys as well. So the common syllabus EC branch and CS branch are having is going to cover today in today's session. Okay, the rest of the CS extra portion is going to cover by tomorrow. So let me get back to you with this question. So important thing here is P1 as a non-pipeline processor, P2 as a 5-stage pipeline with its respective delays of 5 stages, S1, S2, S3, S4, S5. Interface register delay between each stage is 1 nanosecond. So this is uniform interface register delay, but non-uniform stage delays. Okay. So what should be the speed up gain of P2 over P1? So how much gain P2 has over P1 for very large number of instructions? Okay. So to find the speed up gain, there is a direct formula which is n into Tn upon k plus n minus 1 into Tp. Let me have these values explained. N is the number of tasks. N is the number of tasks. Tn is the time taken by non-pipeline. K is the number of stages, and Tp is the time taken by the pipeline. So here we have K as 5, but N is some large number of instruction. So if you look closely, if we have N as a very large value, or 10 to the power 30, or 10 to the power 50, or 10 to the power 25, some large value, the calculation of this particular expression, K plus N minus 1, becomes negligible. So if we have some large number of instructions involved, so for large number of instructions, K plus N minus 1 is actually equivalent to, nearly equivalent to N. So we can ignore this particular expression and just we can use N because it is nearly equivalent to N. So in this particular thing, if you have large number of instructions, N got cancelled. So for large number of instructions, the speed up gain formula, which is denoted by S, is Tn upon Tp. So this particular expression or formula is going to be used only when there are large number of instructions involved. Only when there are large number of instructions involved. Otherwise, this is the correct formula if you have values for stage and the number of tasks. Okay. So then you can use this particular formula. Otherwise, for large number of instruction, the speed of gain is equals to the time taken by the non-pipeline divided by the time taken by the pipeline. Fine. Now, how you are going to calculate these two values? So let me do this calculation here. Time taken by the non-pipeline is actually equals to, because every program is going to take its own time, and you can only have one program at a time. So program one, suppose, or some program goes into the stage one, is not going to get solved parallelly or pipelining or overlapping manner in the next stage. So the total time taken will be in the non-pipeline will be 2 plus 4 plus 3 plus 5 plus 1, because there is no overlapping. So every time the stages is going to execute, the another stage is going to wait before the current stage is going to get the output. Only then it can enter into the next stage, and this cannot have in the overlapping manner. So there is no parallelism or simultaneous behavior. Okay, so the non-pipeline time taken will be 6, then 9 and 10, on total 15. So the total time taken by the non-pipeline is actually 15. This could be in nanoseconds. Then time taken by the pipeline is, now you can have overlapping in here in the pipelining. That is why we are using pipelining to get it processing parallel. Okay, so you can have some simultaneous behavior, but we cannot actually say it simultaneous or parallel processing, because they are actually different, or they have variation uh, as compared to the pipelining. In pipelining, we actually use the overlapping span term. So you can have the programs executed in the overlapping span. Overlapping is like this. So output of one is going to be the input of another. This is what we call overlapping span. Okay, and then if we have some iteration, this is going to be iterate. So the output of last stage is again going to be the input of stage one. This is how it usually works in the pipelining. So in the pipelining, because there is overlapping, the maximum time taken is the time taken by the pipeline. So in here, because we have non-uniform stage delays, so the time taken by the pipeline will be max of stage delays plus register delay or the buffer delay. In place of buffer, we are having interface register right now. So this is the formula to find the time taken by the pipeline. But this will change accordingly if you have uniform and non-uniform delays. So because this is non-uniform delay, for non-uniform, we are having whatever the maximum delay by the actually supported by the or taken by the stage is going to be the time taken by the pipeline and the buffer delay. So because the buffer delay is actually uniform, we are not having the maximum value among this. So this is because it is uniform delay. So this will be, the TP will be equals to maximum stage delay, which is 5 nanoseconds plus 1 nanosecond, which is a uniform delay, gives you 6 nanoseconds of time taken by the pipeline. So let's put it in here. Tn upon Tp, which is actually 15 upon 6, is actually equals to some 2.5. That means P1 here, oh sorry, P2 here is actually 2.5 times faster than P1. So by using the same system as a pipelining, you may achieve 2.5 speed faster than the previous implementation or machine. Okay, so P2 after built as a or upgraded as a pipelining is actually 2.5 times faster than the previous non-pipelining P1 machine. This is the speed up gain. Fine. Again, just write it down or note it down your doubts. We can have it in the later. Okay, we again have a pipelining question, but now this is about the number of cycles required to execute number of instructions. So let me explain this question to you guys first. Consider a 4-stage instruction pipeline with stages IF, ID, PO, and WB. So let me explain this one first. We right now in the pipeline has four stages. IF is actually referred as instruction fetch. ID is instruction decode. In instruction fetch, the instruction is going to get fetched from the memory and to the CPU or for the CPU. Okay, so from memory to the CPU, it is going to be fetch instruction. Instruction decode, whatever the instruction we are fetching are actually encoded in the memory, so we need to decode that first. In the decode section, we actually do the bifurcation of the opcode to find the number of opcodes, or sorry, the type of operation we are having and the number of operands from where we are going to fetch them. So in the decode section, we actually break the instruction format in the known format for the CPU. PO is actually performed operation like execution. Okay, they might use some memory accesses also. And WB is referred as write back. In write back stage, we usually do register read and write operations. Write operation to write it down whatever the output of this particular instruction is, and to read for the next cycle. Okay, so these are the terms of these four stages that is supported by the current pipeline. Instructions I1, I2, I3, and I4 need these stages for execution, supports different number of cycles as given below. Okay, so they usually consume different number of cycles in various stages. For this type of question, it's better to solve it in a tabular form. Now, let me show this particular sample of question, or let me have this in right here. Okay, so these are the number of clock cycles. Okay, and these are the number of instructions we are having in this particular question. I2, I3, and I4. Okay, okay, fine. Let's just have 12 cycles, and if we need it more, we are going to write. So starting from starting from the instruction I1, which is going to enter the stage one first, that is instruction fetch. So let me have some another color. So I1 is going to enter in the first stage, the instruction fetch. The first time in the first cycle or clock cycle, instruction fetch is going to be there for I1. So I1 is going to get fetched first in the pipeline, and then it is going to overlap with the other instructions I2, I3, and I4. Let's see how. Once the IF stages are started for the I1, I2, I3, I4 are basically waiting for their turn. But when I1 is actually complete is going to complete the stage 1 in the clock 1, because it is actually required only one cycle. Okay, so in one cycle it enters into the fetch stage and gets completed, and then eventually it enters into its second stage, which is the decode instruction in the second cycle. But during the second cycle, I2 can enter in the pipeline starting from its first stage, which is the instruction fetch stage for I2. This is what we called overlapping or pipelining. So let me complete I1 first, and then I will show you how I2, I3, I4 is going to execute. So I1, as it is the first instruction, it is not causing any problem. Okay. So one for IF, one for ID, one for performing operation, and two cycles are required for write back operation. So one cycle for performing operation and two cycles are required for write back in I1. Okay, but during the execution of I1, okay, and I1 once enters in the second stage, which is ID, IF is actually free. So IF can be used by the another instruction as overlapping. So hence in the second cycle, once I1 enters into the decode stage, the fetch stage is going to be free, and it is then taken by the next instruction. This is what we called overlapping. This is what we called overlapping. Okay. So for I2, instruction fetch needs one cycle and one cycle for the decode, but two cycles for performing operations. So performing operation will take two cycles, and three cycles for write back. So for writing or reading into the register file will take three cycles for I2 instruction. Fine. For I3, once the fetch stage for I2 is over, the fetch stage is going to be available for I3. But for I3, IF is just will just consume one cycle. So in the second cycle, IF is basically consumed by or occupied by the I2. But in third cycle, IF got free. So IF can be taken by the I3. Okay. So in the third cycle, I3 will take over the IF stage. Once ID of I2 is complete, okay, I3 will take over the next stage, which is the decode. Okay, then two cycles are required for performing operations. But here, performing operation is actually consumed, already taken care by the I2 stage. So PO is not yet free. Okay, so I3 needs to wait for one cycle until PO stage gets free. Okay, this wait or this extra cycle which is created is called stall. This is some extra cycle. Okay, because of some waiting. Okay, so in the performing operations, if you have any extra cycles because of some wait, it is called stall. Fine. So after waiting for one cycle, PO stage got free. Once PO is free, I3 can acquire PO stage for itself. So for PO, it is actually needed two cycles. So PO require two cycles, and then two cycles for the write back operation in I3. Again, write back operation for write back operation, write back is already acquired by the I2 stage. So again, I3 has to wait for one cycle. Okay. So once WB stage is free, it can be acquired by I3 stage. So there will be two stalls during the execution of I3 instruction. Again, let's come to I4. For I4, fetch is going to need two cycles, and fetch stage is going to get freed in the cycle number 4. So up to cycle number 3, IF is being used by I3, but in the fourth cycle, IF is now freed. So starting from this cycle number 4, I4 can acquire the fetch cycle or fetch stage, and it is going to use this stage for two cycles. So IF can be used for two cycles. Then two cycles for the decode. Decode is not overlapping with the above instructions, hence the decode is freed. For two cycles, it is utilized by the I4 instruction. Then three cycles, it is required for performing operations. PO is again freed. It is not going to overlap with some instruction. So we can directly utilize this. And one cycle for write back. And the write back is just got freed in the 10th cycle. Okay. So for 11th cycle, it can be utilized by I4. So I4 got completed in the 11th cycle. So the number of cycles needed to execute I1 to I4 is basically 11 clock cycles. The answer is 11 clock cycles. Okay, so these are called the number of stalls, which are some extra cycles due to some wait or some dependencies. This particular dependency is actually known as structural dependency. This stall is actually being created due to structural dependency. Okay, so in pipelining, we usually have three types of dependencies. So one is structural, where some resources are going to be contradict, okay, or overlapped. If you are having a same stage, if you want to acquire same stage with some another instruction using the same stage in the same cycle, you might have some structural dependency. The structural dependency comes with any functional unit. It could be any memory, it could be any functional unit, it could be any resource. If there is a conflict between two instructions about the same resource, it will be some structural dependency. So this is actually about the number of stages you are having. If you conflict with some instruction for the same resource or stage, it is structural dependency. Another dependency is data dependency. When you want actually you actually want some data for your expression, but that data is actually not overrated or updated by another expression or instruction. So suppose I2 is waiting for some register R0, but R0 is going to update it or is going to get updated in I1, but I1 is not yet completed. So I2 has to wait to get R0 updated. So before I1, I2 cannot get started. So I2 needs to wait until the updation of R0 is complete. These type of data dependencies are usually comes in the gate examination a lot. You might find the number of questions regarding data dependency questions. Data dependency. So data dependency among all the dependencies comes more frequent than the rest. Third one is control dependency. When you have functional conflict with some another, or in simple words, if there is a transfer of control involved, like transfer of control means when the transfer of control executed, the flow of control transferred from one place to another. So control dependency relies on, suppose, structural control structures like if, switch, go to, functions, loops, etc. So wherever these type of expressions or things involved, the control transferred from one section to the different section. In that case, we will have some control dependency. So this is all because of transfer of control operations. If transfer of control operations are there, you might have some control dependency with you. Okay, but in our particular case, in this question given, we only have structural dependency over here. Fine. So this is how you overlap the pipeline and overcome the dependencies. Okay, so you need not to conflict with another instruction for the same stage. So on particular cycle, you cannot have same resource conflict with some another instruction. You need to wait for your turn, and for that wait, it will create some extra cycles, which is called stalls. Okay, which are called stalls. So this third question is actually now completed. The answer is 11 clock cycles are required to execute I1 to I4 based on this given table and consumption of cycles. Okay, let's come to the question number 4. Consider a 32-bit hypothetical processor which is used to execute the following program. Okay, so the program contains number of instructions which are actually I1 to I7. 7 instructions are there in the program that usually take their own size of words. Okay, so I1 is taking 2 words as a size, then some of the instruction take 1 word as a size, and so on. Assume that the program is stored in the memory with the starting address of this 0x334. This is actually some hexadecimal representation of the address. So I1 or this program is going to start with the starting address 334 in hexadecimal. So what could be the value of program counter? We actually need to find the program counter value during the execution of I7 instruction. So what should be the program counter on, or at what address program counter is going to indicate during the execution of I7? Let's get to this thing first. So program counter usually starts with the starting address, and just in the previous question, you have seen instruction fetch stage. Similarly, we have fetch stage in non-pipeline or other simultaneous behavior systems also. So what program counter is used for is it used to indicate the first instruction. Then this first instruction is going to get fetched by the CPU. And once it's fetched by the CPU, program counter immediately incremented its value to the next sequential address. So another instruction is getting pointed by the program counter for the next fetch. Once I1 is getting completed, CPU is ready for I2 operation. So based on program counter value, I2 is getting fetched again. And once it gets fetched, PC again increments to the next instruction, so that we can have the updated instruction in the uh, coming operations. Okay, so for next instruction, PC is already set to the new instruction. This is how it going to works. Once fetched the instruction, fetching the instruction, PC is incremented to its next sequential address or instruction. So during the execution of I7, so after I6, once I6 is fetched, program counter must be pointing to the I7. Once I6 is completed, according to the PC value or based on the PC value, I7 got fetched and started the execution. But during its execution, PC must have incremented to the next sequential address, which is the address from where new portion of memory is going to start. So some another fresh memory block is actually pointed by the PC value, because I7 is already fetched and get into the execution. So once I7 is in the execution process, PC is going to point the next fresh block, which is after the I7. So we need to find out what is that particular block address. Okay. So during the execution of I7, PC must be pointing to the next fresh block. That address we need to find out. So let's start with this question. So during the execution of I7, PC must be pointing to some fresh memory block after I7. Okay. So before starting this particular question, let's have some data. What data actually we have? We have 32-bit hypothetical processor. We have one address or starting address. We need to find the value of program counter during the execution of I7, and this is the program looks like. It has 7 instruction and some size in word for each instruction. Fine. So here the architecture or addressing of memory based on two things. So addressing, let me cover the concept behind this question first, then we can get back to this question. The addressing is of two types. One is byte addressable, and the other thing is word addressable, where if not mentioned, the byte addressable is considered as a default. So as in this question, there is no such information about that the addressing is byte addressable or word addressable. We are going to consider it as byte addressable. Okay. So in byte addressable memory, in byte addressable, the processor we are having is actually 32-bit long. Yeah, or the word length of the processor is 32-bit. Okay. So in byte addressable, one word is actually 32 bits long, is actually of 4 bytes. So we need to convert the word into bytes first, because the addressing in this particular section of question is actually byte addressable. So whatever the configuration of the system we are having here, 32-bit, is actually known as the word length of the processor. So whenever we talk about that our system is 64-bit and 128-bit processor, it is actually the word length of the processor, the length of transfer of word we need to have in the CPU. The CPU can have one word transferred at a time, which is actually bits long. Okay, so the word length of the processor in here is 32-bit. Okay, and the size given in the words, that is why we are going to convert this word into bytes, because the addressing in this particular question is given as byte addressable. So if one word length is 32-bit, this is actually equals to 4 bytes of memory. Okay, so one word transfer at a time, otherwise 4 bytes transfer at the time. So eventually the CPU needs 32-bit memory, whether it is a one word long or whether it is 4 byte long. Okay. So starting from first instruction, I1. Okay. I1 takes 2 word memory. So if one word is 4 byte long, 2 word memory is actually around 8 bytes long. And the starting address of this particular instruction is 334. I'm not writing as a hexadecimal, just uh, get your understanding that how the instructions address are actually changing. So these all values are eventually are in a hexadecimal format. I'm not writing it again and again. Just make it understand. So one word is actually 4 byte long. I1 is already taken 2 words memory. So I1 require 8 bytes long of memory. So 8 bytes will take you 34 to 33B. Okay. So the cell address for I1 storage is starting from 334. So 334 is 1 byte, 335 is another byte, 336 is another byte. Similarly, it is going to be stored till 33B. So it is actually the last digit I'm just explaining here: 4, 5, 6, 7, 8, 9. Then after 9, the hexadecimal value goes as A and B. These 8 bytes: 1, 2, 3, 4, 5, 6, 7, 8. This is 8 byte long instruction. This is going to be stored from 334 to 33B, obviously in hexadecimal format. So this is how the last digit is going to change. Okay. So because it is of 2 words length, I1 starts from 334 and got completed or gets the storage till 33B. So the next instruction, which is I2, definitely starts from the immediate address after I1. I1 is already acquiring 33B. So the starting address of I2 will be 33C. The next sequential address for I2 is 33C. So program counter is starting from I1, which is 334. Once I1 is getting fetched by the CPU, program counter immediately points to the address of I2, which is 33C. Now, the size of I2 is of 1 word. That means 1 word is actually only 4 bytes long. So according to this, starting from 33C, 4 bytes will be C, D, E, and F. I am writing only last 4 values. Oh, sorry, last digit as a incremented values. So this is 4 byte long memory starting from 33C to 33F. Are you getting it? Okay, so I2 got storage till 33F. So from which address I3 is going to get started? So the program counter value for I3 or the starting address of I3 will be 340. The next instruction after 33F. After F, it is going to be 0 again. Okay. So the next instruction address I3 will be starting from 340. Starting from 340, I3 only need 1 word. So 1 word is actually 4 bytes long, which is 0, 1, 2, and 3. This is 4 bytes long instruction. So this is actually going to be 343. Fine. Then let's come to the I4. I4 will have the starting address immediately after the end of I3, which is 344. Okay. Starting from 344, I4 here needs 2 word size. And we already get this understand that 2 word size is actually 8 bytes long. So starting from 4, so 4, 5, 6, 7, just like the above one, 8, 9, then 10 represented by A, and 11 by B as 8 bytes long. Starting from 344, I4 got storage till 340F. Sorry, 340B. Then I5. I5 again, just like I2, it is going to get started from 340C after 340B. Okay. Starting from 340C, I5 needed only one word. Okay, so one word will be C, D, E, F, which is 4 bytes long. So 3, 4, F should be the ending address of I5. Okay, now let's come to the I6. I6, after the I5 instruction, the next sequential address of I6 will be 350. That should be 0 because the last instruction got F in the last value or last address value. Okay, so I5 got completed as 340F, which makes it 350 for I6 instruction. Again, I6, how much it required is actually 2 words long memory. So 2 words long is actually starting from 0 to 7 as 8 bytes long. So this will be 357. After 357, the next sequential address for IS7 will be starting from 358. And from 358, it only required one word memory. This one word is going to get completed as 8, 9, then 10 represented by A and 11 by B, which is one word memory, 4 bytes long. So this will be 3, 5B. So during the execution of I7, the address 358 to 35B is actually occupied by I7. So during the execution of I7, program counter must have incremented to its next sequential address, which could be some any other fresh memory or program. But the starting address of that particular fresh memory will be immediately after the end of I7 address. Okay, so if 35B is the ending address of I7, the next fresh memory block or next sequential address will be 35C. So based on some hexadecimal value, the PC value during the execution of I7 will be in hexadecimal 35C, which is option C. Fine. This is how it is going to execute. So every time program counter starts with some address or starting address instruction. Okay. Once the address instruction is going to fetch, it immediately incremented to its next sequential address. So whatever you are seeing here, the starting address of each and every instruction, these addresses are actually known as NSA, which means next sequential address. Okay, so every time program counter points to the next sequential address, wherever the instruction is ending, it points to the next instruction address, which is the starting address of each and every instruction. So the starting address of each and every instruction is the next sequential address for program counter. Based on program counter, CPU starts fetching of instructions. So according to that, this particular piece of segment or program segment will give you 0x in hexadecimal 35C as the starting address. Okay, during the execution of I7. Fine. So this is the output. Answer is option C. Fine. Let's move to the next question. If you still have some doubt, you can ask me in the end of this session, or you can have this video link with you so that you can have this explanation. Try to understand this explanation again and again. Let's come to the next question. Question number 5. This is again based on some total number of clock cycles required question, uh, based on the instructions or type of instructions we are having and the way of operations it is going to use. So we need to find the number of clock cycles required to execute the given program. Okay, so this particular question is based on the addressing mode or the type of operation, that is opcode, or the instruction format. Okay, so the given instruction has five instructions: I1, I2, I3, I4, I5. Okay, I5 is the halt operation. Three registers are given: R1, R2, and R3, and they have their own sizes in word. Okay, the clock cycles required for operations are, so various operations may have a various clock cycle consumption. So this is already given in the question. Okay, so first thing is register to or from memory transfer requires 4 clock cycles. That means if you see this particular expression, consider it as I1. I1 is an expression which is move operation from some memory address 2000 to the register R1. So this is actually from memory to some register or register from memory. So this type of transfer will take 4 clock cycles. Okay, and the size of this particular instruction is actually 2 words. We'll start with this. Add with both register will take 1 clock cycle. So if you see this particular expression here, add, this require 2 register for operation of add sign. Okay, so this add operation will require only 1 clock cycle. And instruction fetch and decode require 1 clock cycles per word. So every word require 1 clock cycle. If you have 2 words, it will require 2 clock cycles. So each word require 1 clock cycle for instruction fetch and decode. So eventually, before getting to the operation, every instruction must get fetched and decode before execution. Okay, so CPU once fetched and decode requires 1 clock cycle per word. So this will require 2 clock cycles for instruction fetch and decode. This will require 2 clock cycles for fetch and decode, and so on. This will require only 1 clock cycle for fetch and decode because the size is only 1 word. Okay, and then we need to find the total number of cycles occupied by this given program segment. So let's start with this thing. These are the important values. So let me have instructions here first. Then the size of those instructions, and then fetch and decode plus execution or execute. So the number of cycles required, we need to calculate. Okay, we need to calculate are based on some fetch and decode and the execution part. So let me draw it first so that we can have the clear view or better view of this particular explanation. Okay, fine. So starting from instruction 1. Instruction 1, which is this particular expression. Okay, so this is memory to register or register from memory instruction. Okay, this will take 2 word size. Because of this 2 word, this fetch and decode will require uh, 1 clock cycle per word. So this is going to be like one clock cycle per word. So because there are two words involved or two word size, this will require two clock cycles for only fetch and decode. For execution, this is going to be like four clock cycles, because this particular expression or operation is register from memory or memory to register operation. This only require four clock cycles. So in addition of four clock cycle, this whole instruction or operation requires six clock cycles. So we need to calculate each and every clock cycles requirement for each and every instruction. Then the total number of clock cycles will be there. Okay. So in I1 operation, six clock cycles are going to require for fetch, decode, and execute. Let's start with another instruction, I2. Okay. I2 again has two word size, and this is again the operation is based on memory to register or register from memory. So we have R0. Okay, so R0 is basically storing some value which should be some address, and based on that address, the memory will pick or fetch some data and transfer it to the R2. So this is again register from memory, and the memory address is somehow stored in R0. Eventually it is going to be the first type of category, which is register from memory or memory to register. Again, because of size 2, this will require one cycle for each word and need four clock cycles for execution, again of 6 bytes, oh sorry, 6 clock cycles. For I3 will have size 2 words, which makes it one fetch decode cycle per word is 1 into 2, and this operation is basically add with both registers. So add with both register will require only one clock cycle for execution, makes it 3 clock cycles. Okay. Next instruction, I4. I4 is now register to memory or memory from register, again required two size. That means fetch and decode will be same, 1 into 2, and because it is registered to memory, this will require 4 clock cycles extra for execution. Again 6 clock cycles in total. For the last halt operation, I5, this halt operation is of size 1 word. That means only one cycles is required for fetch and decode of this halt, and this halt operation doesn't comes in this category. Hence there is no cycle required for stopping the program segment. Okay, so the clarification of number of cycles required to execute halt is not given, hence we will consider it as 0. So 0 cycles are required to stop this particular code segment. Hence the number of total cycle required is only 1. In total, the number of total cycles will be 6 plus 6 12 plus 6 18 plus 4 is 22. So 22 clock cycles are in total required by the given program segment based on their fetch, decode, and execution as per the question given. Okay, fine. So fetch, decode, and execution goes like this. Let me have some pictorial representation how this is actually going to work. So in usual processors that are actually single tasking or not multitasking, the instruction cycle is consisting of two sub cycles. One is fetch cycle, okay, and another is execution cycle. These are the two subcycles that comes in the instruction cycle, the overall instruction cycle. Fetch cycle is responsible for fetching a new instruction and forward to the execution cycle once they fetch and get decodes. So before execution, the instruction must be decoded in the known format by the CPU. After execution, there are two possibilities. There might be a case that the instruction is completed, okay, and stopped, or otherwise it could be some type of iteration which is going to get fetched again. Okay, so there could be some fresh instruction as well as the repeated instruction. Every time, wherever fetch cycle is going to fetch some instruction, it is going to decode it before getting to the execution cycle. This particular instruction cycle, this is actually instruction cycle, but this will only represent for batch systems or single tasking. There's no multitasking involved because we don't have any interrupts right now. Okay, to make it simultaneous processing, we use interrupts in this particular instruction cycle so that we can have parallelism. Fine. So in this particular instruction cycle, program counter plays a very important role to fetch the number of instructions from memory to the CPU. Okay, so this is come like fetch and decode in this particular cycle, number of cycles required, and once it is fetched and decode, execution will require some more CPU cycles. This is already given in the above question or current question. So the answer is actually 22 cycles required to complete this program segment. Fine. Let's move on to the next question. And after this question, we can have some doubts. Okay. So in the given question, the hypothetical control unit supports five groups of mutually exclusive. Remember, mutually exclusive signals. So these are five groups: G1, G2, G3, G4, G5. 14, 6, 1, 24, and 12 are the number of control signals supported by these groups. Okay, so these groups are like one group is for arithmetic operations, one group is for logical operations, one group is for shift operations, another is for transfer operations, another is for rotate operations. So somehow these are divided into various groups, and these are the number of control signals. In other words, number of operations they support in their each group. Find the size of control memory in bytes using vertical programming. Again, very important term, vertical programming. If control unit supports 256 control word memory. These are the important facts regarding this question. Okay, so first of all, what is vertical programming means? So the control unit, this question is actually from the control unit topic. Let me give the brief about this control unit topic, then we can get back to this question. Control unit comes in two variations. One is hardwired and another is microprogrammed. Hardwired is basically used in real time operations or real time environment. Because they are hardwired, they are quite costly and less flexible. So if you want to change something or modify something, it will cost you high. That is why we go for microprogrammed. But microprogrammed comes in another two variations. First one is horizontal Another one is vertical. In horizontal, the control signal representation, the control signal representation is actually 1 bit per control signal. So number of control signals you are having will take the number of bits for their each signal. But in vertical, the control signal is actually calculated as the log of number of control signals at base 2. Okay, so if you have uh, suppose 8 control signals, so in horizontal the length of the control signal feed will be 8-bit long, because 1 bit for each control signal. If there are 8 control signals, 8-bit long horizontal control signal field should be there. But in vertical case, if you have 8 control signal, it will have only 3-bit long control signal field, which is actually the log of 8 at base 2. So 2 to the power 3. So 3 bits will be required to indicate or to allocate or to identify the number of control signals if we have vertical control unit design or vertical programming. Okay, so in this particular case, vertical programming is given, and we need to find the size of control memory, the whole control memory. So let me explain this thing for you. So we are taking this as vertical programming first. Okay, and in vertical programming, the representation of control memory or control word in this particular representation is like this. So one control word is going to represent it as first field, which is for control signals, and the another is for control memory address. So this is actually one control word, and we actually have already 256 control word memory. So if we find the size of one control word, multiply by 256 will give you the total size of control memory. So control memory is actually the combination or set of control words. And one control word is actually divided into two things: control signals and control memory addresses. Okay. So control memory address field and control signal will make one control word, and a number of control word will make the control memory, which we need to find out in this given question. Okay. So the control memory address is actually can be calculated as the log of number of control words at base 2. So the number of control words we already have 256. So this will be equals to log of 256 at base 2, which is actually 8 bits. So 8 bits is the length of control memory address field in the control word. Okay. About control signals, we have this information that the control unit supports vertical programming, and in the vertical programming, okay, in vertical programming in mutually exclusive manner, it is already written in the question that the signals are grouped as mutually exclusive. Okay, so mutually exclusive means one at a time, one group at a time only. Otherwise the maximum set should be the answer. Okay, but because the groups are mutually exclusive, so if G1 is occupied, another set of groups are not uh, known by the system. Okay, so one at a time, only one group can be recognized by the system at a time. So in vertical programming, we need to find the control signal field length, and that can be calculated as a log of control signals, number of control signals at base 2. So this could be like for group 1, log of control signals that are 14 at base 2, mutually exclusive with log of number of control signals in group 2 at base 2, plus mutually exclusive with log of G3, which is 1 at base 2, plus log of G4, which is 24 at base 2, plus log of G5, which is 12 at base 2. Okay, this is going to be the length of control signals in mutually exclusive manner because only one group comes at a time. So log of 14 at base 2, to find the log at base 2 is going to be very simple. Let me give you some tips about this. So log of 14 for base 2 is going to lie between 2 to the power 3, which is 8, to 2 to the power 4, which is 16. So 14 is going to lie between 8 and 16, right? So this should be, so this value should be somehow equivalent to 3 point something. So this value should be more than 3 but less than 4. So this should be some floating point value comes 3 point something, but we cannot have a bit in floating point representation. So we will round off it to as 4, the next higher whole number. Okay, so 3 point something is going to be 4 bit because 3 bit in total, and the point fraction part will going to be or will going to acquire the whole bit. So 3 point something is going to be number of bits as 4. So this is how we can solve the log problem. Hence log 14, which comes between 2 to the power 3 and 2 to the power 4, makes it 4 bits long. Log of 6, it will lie between 2 to the power 2, which is 4, and 2 to the power 3, 8, between 4 and 8. So it is going to be like 4 point something. So 4 point something we can consider it as, sorry, 2 point something is consider it as 3. Okay, so again for 6 I am explaining. So this will lie between 2 to the power 2, which is 4, from 2 to the power 2, 2 to the power 3, which is 8. So 4 to 8, the value should lie between 4 to 8. So this will be between 2 to 3. So 2 point something is going to be 3 in our case. Okay, otherwise you can calculate it by using some scientific calculator. Fine. Log of 1 at base 2 becomes 0, but because there is one control signal in this group, it will at least utilize one bit. So you can't consider it as 0, because if you consider it as 0, this group is going to be excluded, but we need to include this group. Hence it will require at least one bit of control signal field. For log 24, 24 is going to be like 2 to the power 4, which is 16, to 2 to the power 5, which is 32. So it will be 4 point something, which makes it 5 bits, plus 12 is from 2 to the power 3 to 2 to the power 4. So 3 point something makes it 4. So in total, 4 plus 3 is 7, and 8 plus 9 is 17 bits are required to list these number of groups as a control signal field. So 17 bits long should be the control signal field, and 8 bits long should be the control memory address field. Okay, so in total, this control word has 25 bits length. Okay, so this control word is of 25 bits length, and the number of control words you are having are 256. So the size of control memory okay, the size of control memory, but you need to find this in bytes. So the size of control memory in bytes must be the number of control words multiply by the control word length, each control word length, which is 25 in bits. Okay, So to convert it as in bits, you need to divide it by 8. Okay. So by calculating this, you can calculate this, you will have the answer as 800 bytes. So this should be the length of the whole control memory. This control memory is recognized by or as RAM. Sorry, ROM. So control memory, in other words, in simpler way, you can say it as ROM, the read-only memory. So read-only memory is also known as control memory. So this is how you can find the size of ROM, which is the set of control words, and each control word has some representation based on control signals and control memory address. Okay. So now we can have some doubts. If you have any doubt regarding these 6 questions we just discussed, please let me know. Or otherwise, I will explain you the pointer question I just gave in the starting of the session. So let me have some doubts, or let me ask you question by question. Do anyone have any doubt regarding the question number 1? If anyone is facing some trouble with the question number 1 or explanation, please just let me know. I'll explain to you again. But to go with the questions or numericals, you must have the thorough knowledge of concepts behind this question. So first read or learn about the concepts first, then go for the questions. Otherwise, you will feel demotivated, because the question might get lengthy, but it is simple if you know the concepts behind these questions. So first you go for learning the architecture, then go for the solving the architecture numericals. Otherwise you will be demotivated, because there is hell lot of things to learn and remember. There are a lot of things to remember as well, and there are a lot of formulas, especially for CS guy. Okay. So if you have any doubt regarding question number 1 to 6, just let me know. Okay, there must be some delay in this streaming, that is why. So I'll just wait for 1 or 2 minutes so that we can have some doubt over here. Otherwise, I'll explain the first question, this particular pointer question I just mentioned in the starting of the session. So Shamli is asking this last question. Mutual exclusion is given, so why are we not taking the largest number of control signals instead of adding all the control signals? Because of let me go to this question particularly. Okay, because of this particular term, mutually exclusive, what do you mean by mutually exclusive? That only one thing can go for the execution or some operation at a time. Because this mutually exclusive, you must have heard in the operating system as well. Because of semaphore involved, uh, and the resource conflict is there. So as per the operating system, no two processes can acquire same resource at a time. If they does, the changes by one process will reflect to other and vice versa. So this will create the conflict. In other words, in control, sorry, in our architecture, this is going to be structural dependency, because some resource is going to be get conflicted by number of processes. This shouldn't be happening. Otherwise, there will be some problems or changes in the value. Okay, to overcome this situation, we follow mutual exclusive manner or mutual exclusion. Mutual exclusion is the concept behind this particular problem, is actually saying that one process or one program can only use one resource at a time. So because the mutual exclusive signals are given, we are adding these signals by taking logs. Otherwise, we should take the highest value and take a log of that value, like 24 log at base 2, and that should be our answer for control signals. Because of mutual exclusive given, we are taking these logs and adding them together. Any other doubt? Or should I explain the first programming question? Streaming might have some delays. Just let me know. Shall I explain the first pointer question? Okay. Okay, Saban. Let me explain this particular question for you. So let me have this question somewhere else so that we can have here. Okay. So it's a very simple question based on pointer, but uh, in the background and behind, it is based on the architecture case. So in architecture, there are two type of addressing we already discussed. One is word addressable and another is byte addressable. Okay, this particular question based on architecture is about byte addressable memory. If there is word addressable memory, this question will be simple pointer question. Okay, but if there is some byte memory addressing, so let me get to you that what is word addressable and what is byte addressable in simple example. So if we have some microprocessor and memories as byte addressable memory and word addressable memory. Okay, so let we have some processor as a configuration as suppose 8-bit microprocessor. So in 8-bit microprocessor, this 8-bit is the word length of the processor. One word length is 8-bit. So in word addressable memory, One word length is depending on the configuration of the processor. If the processor is 8-bit long, the word size is 8-bit long. If the processor is a 16-bit long or 16-bit microprocessor, one word length is a 16-bit. So every time when you fetch something, you only need to transfer one cell at a time, because one cell is only the word length of the processor. So if the processor needs 16-bit, the one word is only capable to get transferred. Okay. So if a processor needs to fetch something, only one cell is required to transfer it to the processor, because one cell length is 16-bit, which is equivalent to the word length of the processor. So if this is 32-bit long microprocessor, the word size will become 32-bit. So as you see, this word addressing memory are basically flexible and depend on the word length of the processor. If this is 64-bit microprocessor, word length is 64-bit. Okay, but in byte addressable, byte is already or always referred as or already denoted as or equals to 8 bits only. So whether the processor configuration is changing, the byte will remain 8 bits long only. It is not going to increase in any of the architecture. Okay, so based on any configuration of the processor or word length, byte addressable memory will give you the cell size of only 1 byte, which is 8-bit. So these are the variation we are having in the cell size, because the RAM is set of cells. Each cell is depending on the byte addressable memory and word addressable memory. If the addressing is byte addressable, the cell size is fixed as 1 byte, which is 8-bit. And if the cell size is based on word addressable, it is basically depending on the word length of the processor. If the processor configuration is changing, the cell size is changing in word length, sorry, word addressable memory. So BAM is actually the fixed length, and WAM is actually variable length, or you can say uniform or non-uniform. Okay, so cell size varies based on what type of addressing you are using. So if we ignore this word addressable memory, let's come to the byte addressable memory. This is going to be used in this particular pointer question. Okay, now let me take this thing to different place so that we can have vacant space over here. Fine. So if we take this as byte addressable memory, and suppose if the processor is a 16-bit microprocessor, and this processor needs to fetch some instruction, but the instruction stored in the memory, suppose I1, will require two cells, each of 8 bits long. Because the processor needs 2 byte of information or 16-bit information, processor need to fetch the same 16-bit information from the memory. So suppose there is some I1 instruction, but because of the word length of the processor, I1 is going to acquire two cells. So it is going to acquire two cells, which is equivalent to 16-bit, which is equivalent to the word length of the processor. So because the configuration of processor, the number of cells transferred is going to increase. So in other words, if there is a need to transfer number of cells to the CPU, okay, the addressing is definitely byte addressable memory. Or if you have addressing as byte addressable, there is need to transfer more number of cells, okay, to the CPU. Because in WAM, word addressable memory, the configuration of processor and the cell size is same. So every time you need to transfer only one cell. But in case of byte addressable, if the processor configuration is changing, there might be the situation there where you need to transfer more number of cells to the CPU. Fine. So in this particular case, suppose if you have two different values, like one cell is having value 20, another cell is having value 30. So there are two possibilities. So there will be two possibilities. So there will be two possibilities that program counter, starting from program counter, it should point to the first instruction address, but we don't know which way the program counter is going to set. It could be upward to downwards or from downwards to upwards. So program counter uh, way or the direction of program counter may be upwards or downwards. This should be known before the architecture involved. Okay, so before reading any instruction, the program counter must know where should I get to start and from where and in which direction we need to go. So let's suppose, let's suppose two cell addresses. These two cell addresses are 1000, and after one cell, the next instruction address is suppose 1001. These are the cell addresses of 20 and 30, because each cell has its own identification number, which is called an address. So based on program counter value, first thing, where the program counter should need to start and in which direction it is need to traverse. So if program counter starts from 1000, is it necessary it will go downwards, or it might go upward as well? Because if it goes upward, the value should be different, or you will have some incorrect values there. So this should be given by the architecture before the organization. If the ruling is not given, it will make the operations complex and incorrect. To make it correct, one mechanism is given by the architecture, which is called Indianness. Indianness is the concept. Indianness is the concept behind this, which will tell where the program counter need to set and in which direction it is going to move on. Indianness is of two types, which is Little Indian and Big Indian. Little Indian means the least significant bit or lower address. From starting from lower address, you will move to the higher address. And Big Indian means starting from higher address, you will move to lower address. Okay, so every architecture in byte addressable memory use either little or big Indian, like our Pentium or the i5 architecture or i series in the laptops or personal computers follow the little Indian process. You can check this particular code by executing this in some compiler. Okay, it will tell you which architecture is used by, or which Indian NAS is based, or which Indian NAS is actually supported by your system or PC. Okay, so in Little Indian, you will start from the lower address like 1000 to 1001, and if there is a Big Indian, you will start from the higher address, that means 1001, and move on to the or decrement it to the least significant address. Okay, this particular code will tell you what architecture your computer is using, either it is Little or Big Indian. So all we need to do is, like, we have an integer variable a, which is 320 value, and this 320 value is going to be stored in 16-bit representation, because we already taken 16-bit microprocessor. So in 16-bit microprocessor, integer size will be 16-bit long. So this 320 representation will be in 16-bit, which is 2 byte. Okay, but character here, will only can only read 1 byte at a time. Okay, so each byte of a variable is going to be read twice. Sorry, in other words, we can say the whole memory of a is going to be read twice one address or one cell at a time, because A has two cells, but character pointer can only jump one cell at a time. It can only read one cell at a time. So the 320 representation in binary or 16-bit will be 256 plus 64. So this will be 1, 2, 4, 8, 16, 32, 64, 128, and 256. So this will be 1, 2, 3, 4, 5, 6, 7, 8. This is going to be first byte, and the another 8 bit will be like this: 2, 3, 4, 5, 6, 7. This is another 8 bits. Okay, so this is first byte, this is second byte. So if there is a little Indian involved, suppose this is A, so the starting address will be like this. Starting address will be like this. So A memory will be like, suppose the address starting is 100, so next cell should be starting from 101. So for if there is little Indian, the lower bit, which is the first bit, goes to the lower address, and the higher bit goes to the higher address, if this is the case of little Indian. Okay, so if you read one cell at a time, you will have the values as this first byte. If you read it first, will give you the value 64, because it is a binary of 64. And the another bit is only the representation of 1. This representation you will have if you have little architecture. But in case of big Indianness, the second byte goes to the lower address, and higher lower byte goes to the higher address, and you start it from the higher address. If you start it from the higher address in big Indian, the output will be 1 and 64. It will going to be reversed. Okay, so based on the output we can tell which Indianness is supported by our current machine. Okay, just go through with the explanation and try to understand this thing. This is highly conceptual thing. So this piece of code will let you know which architecture is used by your system or computer. Okay, because the time is up, we have to end the session, but I explained it quite fine, so you can have this understanding by uh, streaming it slowly, or you guys have to manage it. But I actually completed this explanation, so there's nothing left about this particular question. Because of time is up, we have to end the session. The next session tomorrow, we will cover the remaining portion of the CS branch. Okay, thank you guys.